Nikolay Bogachev. Our third speaker, Nikolay Bogachev, on geometry and arithmetic of hyperbolic orbifolds.
Thank you very much for the invitation and for introducing me. And I would like to start first from the very broad picture. So what we study in this subject. So I hope you hear me properly, or should I speak more loudly? No?
That's okay, I think.
Okay, great. So we study here geometric group actions of discrete groups, and the group acts on some symmetric space G mod K, where G is the Lie group of isometries of this space X, and gamma is considered as a discrete subgroup of this Lie group. And generally, I usually like to draw this as this triangular diagram, and the this top vertex corresponds to actually algebra and number theory. So here G can be a Lie group like SLNR or SON1R, and the question is how number theory is arise here. Number theory is here actually in matrices. So the group gamma can be described as matrix groups, and for example, if we have some numbers, it can be integer numbers or some other numbers, and that's the place where number theory is in this game. So another part of this picture is actually about geometry and torics. So these geometric group actions, they correspond to nice stylings or tessellations of the space X by convex polyhedra, so-called fundamental polyhedra for discrete group gamma. And all of this is actually related to geometry and topology. And geometry topology meaning a geometry topology of a corresponding orbifold or manifold X mod gamma. A typical example of this is actually the group Z squared acting on the Euclidean plane E2 by integer translations. So here we have a tessellation by squares, by equal copies of squares of this plane, and the square is actually with the identified opposite sides is homeomorphic to the flat torus. So our main goal actually is to focus on to study hyperbolic orbifolds in the view of this picture. And hyperbolic orbifolds are just orbifolds Hn mod gamma, where gamma is, in our case, it's a lattice acting in the hyperbolic n space by isometries. And well, a typical example is here actually also a group which is kind of similar to Z squared, but it is a free product Z times Z. And this is actually an arithmetic group, meaning it's commensurable to the PSL to Z, so to integer group of an algebraic group, to integer points of an algebraic group SL2. Here, this group gamma is generated by two translations along geodesics, as we see it in the picture, and the corresponding fundamental ideal for GON after identifying its opposite sides is actually will give us one cusp hyperbolic surface, which is a torus, one punctured torus actually. So our main goal in this topic, in this talk, is to study the connection, arithmetic properties of hyperbolic lattices gamma and the behavior of totally geodesic subspaces of Hn mod gamma. So I would start first from some preliminary definitions and maybe a couple of some results in like the state of the art of this theory, and then I will move to the main results of this talk. So the talk is based on our recent paper with Misha Belolipetsky, Sasha Kolpakov, and Leonid Slavich. It's called Subspace Stabilizers in Hyperbolic Lattices. But in fact, this talk also is also motivated by some previous results done by me and other mathematicians. So I start from, I think that probably all of the audience is familiar with the definitions of hyperbolic space, but I still will give some definition which we actually use. So we consider hyperbolic space as, we can consider it in the vector model. So we have the Minkowski space Rn1 equipped with a symmetric bilinear form of signature N1, and then Hn is the upper, it is the upper half sheet of the hyperboloid. We can see it like on the picture here, and the hyperbolic metric in this model is given by this equation. There are actually several other models, the Klein model, the Poincaré model, and also the upper half space model. And I would like to probably emphasize that the isometry group of the hyperbolic space, it can be considered as the Lie group On1 plus, which is the subgroup of index 2 in the orthogonal group, preserving this quadratic form of signature N1. But this On1 plus is not an algebraic group, but it can be identified with an algebraic group, PON1, which is On1 mod by the center. So N1 by plus minus identity. And this identification is convenient for our purposes. One more remarks, one can get the following isomorphisms via upper half space model UN of the hyperbolic space. In fact, orientation preserving subgroup of isometries of H2 is PSL to R, and for H3 it is PSL to C actually. Okay, so now let me move to the definition of arithmetic groups. So we would like to study the connection of arithmeticity, so number theory, with geometry and topology. So as I already said in the introduction that arithmeticity is something about integer entries of matrices in our group. It's very rough definition, but algebraic group, arithmetic groups are the groups that can be built out of these fundamental examples, like the group Z acting in the real line, right, by just integer translations, or this example with the fundamental group of the torus, the square acting by integer translations in the plane. So very broad definition. Well, it's not very concrete, but so we need to have some algebraic group, for example, over Q, and we should take it integer points. So typical examples of arithmetic groups are PSL to Z acting in the hyperbolic plane, or SLN Z as a subgroup of SLN R, etc. The natural question is why they are really interesting. Actually, arithmetic groups are lattices, meaning that they always have a finite volume fundamental domain in the corresponding space. In the general theory of discrete subgroups of Lie groups, this means that so the group, any logical group G actually has a Haar measure, left invariant Haar measure on G, and gamma is called the lattice if the G mod gamma has finite this projected Haar measure on this quotient. In our case, is equivalent to the fact that the fundamental domain has finite volume. Uniform lattices correspond to co-compact groups. So Hn mod gamma should be a compact polyhedron. Well, generally it's a manifold or an orbifold. And it is equivalent to G mod gamma being compact. So here in this picture, actually I presented both uniform reflective lattices. So we can consider a group generated by reflections in a single triangle, and then we'll get a uniform lattice generated by reflections in lines. So also, well, I think that everyone is familiar with the commensurability notion, but let me give some, well, just to repeat this definition. So we say that gamma 1 is commensurable with gamma 2 if the intersection is a finite index in both. And we are also interested in commensurability in the wide sense, which means that they are commensurable up to conjugation by some element, up to conjugation by the element of some of this isometry, full isometry group of the hyperbolic space. And so an important remark is that if you have two commensurable lattices, actually even groups, then if gamma 1 is discrete or a lattice or a uniform lattice, then gamma 2 has the same property. Actually, yeah, here I have also one nice example. For example, we can consider a group generated by reflections in sides of an ideal triangle, and it is commensurable to the group generated by reflections in this triangle, and all these groups are commensurable to PSL2Z. So actually, all these groups are arithmetic. But I would like to give a more general definition of an arithmetic group, and here we need a totally real number field and its ring of integers. So for example, one can think about the field Q over root 2, so consisting of these numbers, and the corresponding ring of integer then will be just Z over root 2. And let G be a non-compact semi-simple Lie group such that G, so its connected component, has no compact factors. By definition, an algebraic K group G tilde is called admissible for G if there exists a surjective homomorphism from this product to our group G with compact kernel. So what does it mean, this product? So we have here G sigma, G tilde sigma, and our G tilde is given by a set of the set of polynomials over the field K. So we can think of like the system of polynomials, and our actually G tilde is just the set of solutions, right, for this system of polynomial equations. But then we can apply all non-identity, actually all embeddings of the field K into R, and we should apply the sigma to all the coefficients of the polynomials of G tilde. So we will have exactly as many here components in this product as the degree of the field K. So in this particular case, when K is Q over 2, in this case we will have just two components in this product. So it will be G sigma 1 product G sigma 2, and we take real points of that. So this product should be so up to actually this means that it is isogenous to our Lie group G times compact kernel. So the very important theorem of Borel and Harish-Chandra says that if if G tilde is an admissible algebraic group for the Lie group G, then the group of integer points is always a lattice in this product and actually in the group G, in the Lie group G. So again, some examples are here. SL2Z is a lattice in SL2R. And for example, SL2 taken in these points, so we consider the matrices with entries Z over root 2. In this case, we will get actually a lattice in the product SL2R, SL2R, since since we can get back to this definition, we have here two components in this product, and in both of them are non-compact. So actually, we can observe that SL2Z over root 2 it's dense. It is dense in SL2R itself, but it can be discretely and very good embedded in the product. So this will be lattice here, and there is also another general set of examples coming from quadratic forms. So we can consider a quadratic form, and we can also take the group of automorphisms of this quadratic form. So we just take all the integer transformations preserving the matrix of the quadratic form, and in this case we will get also an arithmetic lattice sitting in SOFR. So it is now we understand that arithmetic groups are lattices, but it's very interesting to pose the opposite question: if we have an irreducible lattice, then is it arithmetic or not? And in approximately about 1974, Margulis proved his famous superrigidity and arithmeticity theorems, and generally states that if gamma is an irreducible lattice in the Lie group G, and the real rank is greater than 1, then gamma is actually arithmetic. So more precisely, G shouldn't be isogynous to SON1R or SUN1. And this corresponds to the isometry group of the real hyperbolic space, and this corresponds actually to the isometry group of the complex hyperbolic space. In all other settings, Margulis arithmeticity theorem holds. And this gives rise to a very rich theory of arithmetic and non-arithmetic lattices in hyperbolic spaces. One more also very important theorem, also proved by Margulis, it is Margulis commensurator rigidity. And it states that if gamma is a lattice, then we can consider its commensurator right in the Lie group G. It consists of all such G that the conjugation of gamma by G is commensurable with gamma. So then gamma is arithmetic if and only if this commensurator is dense in G, and gamma is non-arithmetic if and only if the commensurator is a lattice in G. And moreover, this commensurator of gamma actually is a lattice containing G, and it will be a maximal lattice containing, our group gamma. Well, here I just left a few more examples of arithmetic groups from quadratic forms. I think that I won't stop here, but I can just say that some of these examples also correspond to PSL2Z. So we just see PSL2Z as a matrix algebraic group with taken integer points, but we can also consider a particular quadratic form, and actually the isometry group of this quadratic form, more precisely SO plus F1. Sorry?
вчера, может быть, ты убирал что-то.
Ничего не убирал.
Sorry, I can
Sorry,
continue.
ничего нет.
So,
Oh, you unmute.
Nikolay, could you please turn your sound on again?
Is our sound on?
Yeah, thanks. Yeah, you're good.
I'm here, or
Yes.
You're here.
Yeah,
okay, great. Thanks. Yeah. So, just one remark about this quadratic form. So, if quadratic form is isotropic over Q, meaning is that it represents zero. In this case, it's this the corresponding isometry group of this quadratic form will give us non-uniform lattice. So we will have ideal vertices of our fundamental domain. It won't be co-compact. But if f of x is anisotropic over the field, then we will have a uniform lattice. And moreover, this quadratic form should be also admissible. So in fact, if the field is of degree greater than 1, then we will have always uniform lattices. So non-uniform lattices, it is a well-known statement that non-uniform lattices are always defined over Q, and actually they are of this simplest type. So they are known to be as group of units of quadratic forms over just rational number field. So, but let me now, well, maybe at this point, should I ask that if there are some questions, then I'm ready to answer, since now I'm going to.
Yeah, if you go back a few slides, there was this question about, right, you gave, I'm trying to remember, you gave a notion of commensurated, and then I forget the word you used for, right, when you're actually commensurated by some conjugator.
Commutator, no?
So, no,
Here?
I think right, you gave some, right,
Or this one, no? Commutator?
Okay, sorry, yeah, so I guess, sure. So what conditions do you need on a G for commensurated rigidity? Is it also need to be semi-simple Lie group of rank at least 2, or is this true?
Well, yeah, that's the good question. Actually, no, it's this theorem works also for real hyperbolic spaces and for complex hyperbolic spaces. So, yeah, this is actually very helpful and even for our purposes. Yeah, this theorem works in rank 1 case 2, but the above theorem doesn't work in these cases. So yeah, it's very nice that yeah, it's indeed very I mean, so the behavior of commutator is very rigid. So it's either a very dense group. In fact, in the arithmetic case, it contains all rational points of the algebraic group G tilde. So it's indeed very dense in our Lie group G, but in the non-arithmetic case, it will be just a lattice, maximal lattice containing our lattice gamma. So gamma will be a finite index in the commutator. So now, yes, and now I would like to move to the main results of our paper, and we need the definition of a totally geodesic subspace. So we say that suppose we have two hyperbolic orbifolds, Hn mod lambda and Hm mod gamma, and we say that this map is a totally geodesic immersion, and actually we need proper. So we need proper immersions. So if any of its lifts to HN map to HM, it will map this plane HN to an n-dimensional plane in the bigger hyperbolic space. So it's equivalent to the fact that there exists an n-dimensional plane such that the stabilizer of this plane in the lattice gamma here, it will be a subgroup of this product PON1 times compact factor. This compact factor is actually consists of all rotations, like all finite. Well, it's a compact group preserving our plane, right? And this stabilizer, it should act as a lattice on this plane U, and the projection on PON1 will be isomorphic to the lattice lambda. So these are properly immersed, totally geodesic subspaces. Examples are, like, for example, these are geodesics in hyperbolic surfaces, or some number of examples can be extracted from Coxeter orbifolds. Coxeter orbifolds are actually reflective orbifolds, so we can consider lattices generated by reflections in facets of Coxeter polyhedra. These polyhedra should have dihedral angles of the form pi over some integer, over some pi over 2, pi over 3, or so, and geodesic, totally geodesic lines, for example, in this reflective corresponding orbifold can be viewed as just this polyhedron with reflective singularities in these facets, and this means that actually totally geodesic subspace will be a closed, it will be a closed billiard trajectory in this polygon or polyhedron. And a very particular example is that if you have a side, for example, which has right angles with adjacent sides, in this case, this will be just a totally geodesic subspace, since you will bounce between these two sides, and that's it. So we study these objects. Then I want to introduce the main notion of this paper. An immersed totally geodesic suborbifold N is called NFC subspace, as we can be witness finite centralizer subspace if there is a finite subgroup of commutator. So yeah, two other FC, so here F and here commutator. So there is a finite subgroup of commutator such that the plane U is a fixed point set of this group, and it is a plane of any dimension in the hyperbolic space HM, which corresponds to an ambient manifold or orbifold, and our subspace, our suborbifold, is the quotient of this plane U by the stabilizer of the plane U in the lattice gamma. So in our paper, we first show that, well, not first, but one of the theorems, it shows that if gamma is a uniform or non-uniform lattice and F is a finite subgroup of commutator with a fixed point set of dimension at least 2, then the stabilizer of U and gamma acts as a lattice, respectively uniform or non-uniform, and this actually, so this theorem roughly says that states that we indeed obtain a totally geodesic, properly immersed hyperbolic suborbifold in our ambient hyperbolic orbifold. Here I would like to say a few words about motivation of this definition. For example, let us consider again a finite volume Coxeter polytope, and if F is its face of codimension 1 with even angles with all edges and faces. What are these even angles? These are angles like pi over 4, pi over 6, so pi over some even number. And these angles shouldn't be equal to each other. They can be different, but still they should be even, like some of them can be pi over 2 and pi over 4. In this case, we have this blue hyperplane. So I have this picture, and for example, here are angles pi over 4, but this means that we actually have in this group gamma, in the group generated by reflections in P, we have also reflections in blue hyperplanes with respect to blue hyperplanes. And these blue hyperplanes, they are orthogonal to the supporting hyperplane of this facet F. And these reflections, which are orthogonal to the hyperplane U, they preserve actually this hyperplane, right? So the group generated by reflections in this, just in this blue hyperplanes, orthogonal to our fixed hyperplane U. This intersection will cut in the hyperplane U also a good Coxeter polyhedron, and actually this will be just a facet F itself. And this is just a very particular example of the definition above. So we have the hyperplane U, and it is actually fixed by the reflection. So this reflection is sitting in our gamma P itself, and so of course it is contained in the commutator. Also, another motivation for this definition is symmetry. So we can think of symmetries of orbifolds. So for example, we have some orbifold which is symmetric to with respect to reflection in hyperplane, and in this case, as it is drawn in the picture, we have a reflection which, so it will correspond to an FC subspace, since the corresponding reflection is contained in the commutator of gamma P. So when you have a symmetry, you are definitely sitting in the commutator. And also there are kind of hidden symmetries, which are symmetries of some finite covers. I tried to illustrate this definition of hidden symmetry by this picture. So we can have a geodesic line, which is not a symmetry of a particular fundamental domain here, which is a square, but it will be a symmetry of the finite. Well, I'm not sure that but I just wanted to give you an idea. So we may have no symmetries of the orbifold P1 itself, but we may have symmetries of finite covers, and this is okay. So this will also give us an FC subspace of one ambient hyperbolic orbifold. So the main theorem then states the following: let M be a hyperbolic orbifold of finite volume, and then M is arithmetic if and only if it has infinitely many FC subspaces. Moreover, in the arithmetic case, any totally geodesic suborbifold of dimension at least M over 2, well, actually 4 M over 2, should be FC. But in higher codimensions, so smaller codimensions should be always FC in the arithmetic case, but small dimensional can be non-FC actually. So there are some examples. Moreover, M is non-arithmetic, of course, if and only if M has only finitely many of FC subspaces, and in fact, the number of these FC subspaces can be bounded above by some constant depending on the dimension multiplied by the volume of the hyperbolic manifold or orbifold M. Here one of the other results of this paper, we show that Gromov, Petesky, Shapiro, these are famous non-arithmetic hyperbolic hybrids constructed by Gromov and Petesky, Shapiro. They are constructed as gluings of incommensurable blocks M1 and M2. So the corresponding lattices gamma 1 and gamma 2 shouldn't be commensurable. They are not commensurable. But in this case, we can get non-arithmetic hyperbolic orbifold. These are glued along the common totally geodesic boundary, and actually this is totally geodesic boundary of codimension 1, and these hyperbolic surfaces, these gluing locus, always are non-FC subspaces in all Gromov and Petesky Shapiro hyperbolic hybrids. This example is kind of, it refers to this bound. So in the arithmetic case, we cannot have such kind of examples. In non-arithmetic, we see these examples. As a corollary of our theorem, we obtain the following: if H, so it is known that H, there are some hyperbolic 3 orbifolds or manifolds that contain no totally geodesic surfaces, but they always contain geodesics. And our theorem actually covers this case. So M is arithmetic if and only if it just contains infinitely many FC one-dimensional geodesics. And in the arithmetic case, all properly immersed surfaces and geodesics should have this FC property. Now I should say a few words about the state of the art and what was proved before about that. I mean, actually the question of detecting arithmeticity through just geometric properties of hyperbolic manifolds, it seemed to be a very hard problem. It has remained open maybe for several decades, but recently several revolutionary solutions were suggested to this problem. In the dimension 3, it was proved by Margulis and Mohammadi about 3 years ago. The paper was submitted to archive, and almost at the same time, a bit later maybe, Bader, Fisher, Miller, and Stover proved this, proved the theorem, a similar theorem for hyperbolic manifolds of all dimensions. What do they prove exactly? They prove that if a hyperbolic manifold finite volume contains infinitely many maximal geodesic subspaces, then it should be arithmetic. So this is a bit different from what we prove, and actually the methods are very different since they use some kind of new super rigidity theorems, and moreover, so for example, they discuss only the case when you have infinitely many surfaces. So starting dimensions at least 2, right? So we should have maximal, infinitely many maximal totally spaces of dimension 2 and higher. But as I said, there are some examples when you have only geodesics but not surfaces. And in fact, I think that in the early 90s, Alan Reed proved that if a hyperbolic 3 manifold is arithmetic, and if it contains one surface, then it contains infinitely many of them. So it kind of, it is kind of very natural to ask if the opposite is true. So if you have infinitely many surfaces or geodesics, then is your manifold arithmetic or not? And Alan Reed, I think he proved, so as I understand, he proved exactly, he proved exactly this statement for arithmetic, for hyperbolic 3 manifolds. So he showed that there are infinitely many FC geodesics. He called it, yeah, in a bit different terms, but it is equivalent to what we proved. Well, but our, I mean that this corollary is really just a very simple corollary of our main theorem. And I think I have maybe just a few minutes to say a few words about the sketch of proof. And the proof is based on several considerations on the following things. So first of all, in the arithmetic case, we should really construct this finite order element sitting in the commutator. So we should produce finite subgroups of commutator, and actually then we should get infinitely many of them. So we did it for each type of arithmetic lattices. There are generally 3 types of arithmetic lattices in hyperbolic spaces, and so we found these k-defined involutions in all the cases, and this is just enough. So after we have this k-defined involution in the commutator, then you can, using Margulis commutator rigidity, you can get infinitely many such subspaces. But another part of this theorem is already hard. It is based on careful work with Weinberg's commusurability invariance, a joint trace field K, and an ambient group G tilde. And we also study immersions of arithmetic hyperbolic orbifolds into one another. And I think that I can say just what we, I mean, what is the main theorem behind this proof. So what became surprising that if we have an arithmetic orbifold with defined over some field Km, and we have this properly immersed totally geodesic suborbifold N, it turned out that the joint trace field of suborbifold can be larger than the field of the ambient manifold. So there are 2 types of suborbifolds: subform space, we call it if the field coincide, if the fields coincide, and we call another type the Weyl restriction subspace if the field can be bigger. And we provide some examples when we really have bigger fields of suborbifolds. The theorem in our paper states that actually for any properly immersed totally geodesic subspace of an arithmetic hyperbolic orbifold, so we have N sitting in our hyperbolic orbifold M, then if we can, so we suppose that the joint trace field of smaller orbifold has degree d over k over small k, then we show that there exists a unique minimal subform space here containing n such that there are no proper subform spaces of S containing our n. So there is a chain of inclusions, right? And S, this inclusion is it corresponds to subform spaces when the field is the same, but here already the field can become bigger. And so roughly speaking, it means that we have either these 2 types of arithmetic immersions or the combination of these 2 types. And again, we provide examples, and here we also see some particular, so the dimensions are can be computed if the degree is greater than 1. And yeah, we have more examples in the paper. I think that I should stop here. So thank you very much for your attention, and yeah, thank you.
Any questions for the speaker? Perhaps, again, we can start with the Zoom participants. Are there questions on Zoom?
Maybe, Rachel, maybe you can ask the question in the room and.
Yes. Are there questions in the room? All right, I think no questions. Yes. So let's just thank Nikolay one more time. Yeah.
Thank you, Nikolay, for this talk in a bit difficult circumstances, but it's great that you were with us finally.
Yeah, thank you very much. And yeah, so for these technical issues, well, I have a very old computer actually.
Yeah. We're just glad we had you, even though, you know, you're in the middle of a chaotic move and things.
I don't have questions right now. Maybe I will have to think actually before you ask me some questions.
Yeah,
but
sure. I'm ready to respond. Of course, please write me an email, and if you have questions, no problem.
maybe let's thank the speaker again. So also in the room, right?
Thank you.
Yes.